if you took the smartest artificial intelligence in the world right now,
Mm.
the ones that are, writing code or passing medical board exams, summarizing giant legal briefs.
Right, the really massive digital brains.
Exactly. If you took those and stripped away just one specific conceptual breakthrough that was published in 2017, those massive systems just, well, they would be able to string together a single coherent paragraph.
Yeah, they'd be completely useless.
Right. And, walking into the world of AI right now, it feels a bit like walking into a massive echoing library where everyone is just like shouting in acronyms.
Oh, absolutely. It's LLM this, RLHF that.
Yes. RA, scaling laws, PPO. And for you as someone who loves to learn but absolutely hates information overload, you've probably felt that that familiar wave of panic.
It's incredibly noisy out there.
It is. You want to understand the magic behind the curtain, but you don't want to read a 1,000-page textbook to get there.
And frankly, I mean, a lot of the conversation out there focuses on the hype rather than the actual mechanics. It's so easy to get lost in the endless news cycles and just, lose sight of the foundational science that makes all of this work.
Exactly. Which is why today we have a very specific mission. We're going to cut straight through that noise. Using a brilliantly curated reading list from Katie Nuggets by Kenwal Marine, we're going to dive into 5 foundational research papers.
And these aren't just any papers.
No, they're the exact blueprint of how modern AI actually works. We're going to summarize and focus on the most impactful insights.
Yeah, we're going to trace the scientific evolution step by step, just looking purely at the insights that got us to where we are today.
So we'll start with the underlying architecture, like the engine. Then we'll look at the sheer brute force of scaling it up.
Right, the fuel.
Yeah. After that, we had to talk about how we teach the AI some manners so it doesn't just, parrot the absolute worst, most unhelpful parts of the internet.
Which is a crucial step.
Very. And finally, we'll look at how we give it a reference library so it stops confidently making things up.
Yeah.
So, okay, let's unpack this, starting at the very beginning. The engine.
Right. So if we want to really understand the current AI revolution, we have to go back to that 2017 breakthrough from the Google researchers.
The famous one.
Yeah, the paper is titled, "Attention is All You Need." And to understand why it changed everything, I mean, you kind of have to know what came before it.
Right.
Before 2017, the dominant way to process language was using recurrent neural networks, or RNNs, and occasionally convolutional neural networks, or CNNs.
And from my understanding of the sources, convolutional networks, the CNNs, they're great for looking at grins of data.
Like images.
Right, like recognizing edges and shapes in a photo.
Yeah.
But they really struggle with the flowing sequential nature of text.
Exactly.
So that left the whole industry relying heavily on those recurrent networks, the RNNs.
Precisely. But the problem with RNNs is that they process text sequentially. I mean, they read text exactly the way we do, word by word, left to right.
Okay, so step 2 cannot begin until step 1 is completely finished.
Exactly. And in computer science, sequential operations are just a massive bottleneck. You can't parallelize them effectively across modern hardware.
Like GPUs.
Right. GPUs are designed to do thousands of calculations simultaneously, but RNNs force them to work one word at a time.
It's like reading a book through a tiny slit in a piece of paper. You can only see the current word, and you have to somehow hold the memory of all the previous words in your head just to understand the end of the sentence.
That is a great way to put it.
So is this new attention mechanism just like having multiple pairs of eyes looking at an entire page at once so you instantly map out the connections?
Actually, that's a pretty common misconception.
Oh, really?
Yeah. It's not just about looking at the whole page simultaneously. It's about actively, mathematically weighing the relevance of every single word to every other word, all at the exact same time.
Okay, so how does it do that?
The architecture they introduced, which is called the transformer, uses something specific called scaled dot product attention. Instead of scanning a sentence, it relies on 3 interconnected concepts: queries, keys, and values.
Okay, that sounds heavily mathematical. I want to make sure we're translating this clearly for you listening. If it's not just multiple eyes, how do queries, keys, and values actually work? Like, is it like a retrieval system in a library?
Think of it exactly like a library retrieval system. Imagine the word the model is currently trying to understand is the query.
Like a search term you type into a database.
Right. And then every other word in the sentence acts as a potential tag, which we call a key. The model calculates how closely the query matches each key.
Oh, okay.
And when it finds a strong match, it extracts the underlying meaning, which is the value.
Ah, I see. So if you have the sentence, "The bank of the river was muddy," The word bank is the query. It checks the keys of all the other words. And when it checks river and muddy, the mathematical match is incredibly strong, so it pulls the value of a muddy riverbank.
Wow.
Rather than like a financial institution.
Exactly. And it does this for every single word in the sentence simultaneously.
That's wild.
And what's fascinating here is that the Google researchers didn't just stop at one attention mechanism. They realized language is incredibly complex, so they introduced multi-head attention.
Multi-head, meaning what exactly?
In their base model, they ran this entire query key value process 8 different times in parallel.
8 different heads doing the exact same thing. Wait, why wouldn't they just get the same result 8 times?
Because the network learns to specialize them. These multiple heads track totally different aspects of the text.
Oh, I see.
Yeah, so one head might focus entirely on syntactic structure, making sure the subject and the verb agree. Another head might ignore grammar completely and just track semantic relationships.
Like figuring out who the word she refers to in a really long paragraph. That's brilliant. So it's not just reading fast, it's analyzing the sentence from 8 different linguistic perspectives at the exact same time.
Right.
And because it's not reading left to right, you don't have to wait. You can just throw massive amounts of parallel computing power at it.
And the results vindicated the theory entirely. On a standard English to German translation task, this new transformer model achieved what's called a BLEU score of 28.4.
A BLEU score.
Yeah, BLEU stands for Bilingual Evaluation Understudy. It's just a metric used to compare machine translation to high-quality human translation.
Got it.
Now, hitting 28.4 might not sound like a huge number out of context, but it beat the absolute best existing models by over 2 full points.
Which is huge.
It's a massive leap in this field.
And the truly wild part to me wasn't just that it was better, it was the efficiency. The paper notes. They achieved this after training for just 12 hours on 8 P100 GPUs.
Yeah.
12 hours. I mean, that's basically a coffee break in the world of machine learning.
It really is. By removing the sequential bottleneck, they built this incredibly fast, highly efficient engine. But as with any major engineering breakthrough, human nature took over.
Naturally.
Once researchers realized how scalable this engine was, they immediately asked a new question. What happens if we take this exact architecture, don't change the underlying math at all, but just build a ridiculously massive version of it?
Which brings us to the second massive phase of our deep dive. We have the engine. Now, we talk about the fuel, and this is where we get into the era of scaling laws.
Yes. To understand the sheer scale of modern AI, we turn to 2 critical papers from OpenAI.
Okay, what are they?
Scaling Laws for Neural Language Models and Language Models are Few-Shot Learners, which is the paper that formally introduced GPT-3 to the world.
So I read the scaling laws paper, and I have to admit, it kind of bothered me a bit.
Yeah, why is that?
Well, they essentially set out to find the physics equations for AI, right? They wanted to see what happens when you throw more data and more compute at this transformer engine. But they found that elegant software architecture just barely matters.
It's true.
The depth of the neural network, the width, the exact number of attention heads, none of it drastically changed the outcome compared to just making the model bigger. I mean, are we really saying that in advanced computer science, brute force just straight up won?
I completely understand why that feels frustrating. I mean, it goes against everything we assume about elegant software engineering.
Right. We want the cleverest code to win.
We do. But the paper proved, mathematically, that raw scale dominates. They studied the cross-entropy loss, which is basically a technical way of measuring how often the AI is surprised by the next word it sees in a text.
Great.
The lower the surprise, the better the AI understands language.
Right. And they found that this loss decreases predictably based on a power law relationship. It's all about 3 factors.
Exactly. The number of parameters in the model, the size of the data set, and the raw compute used for training.
And the math they discovered is incredibly reliable, right? But it contains a very important caveat, from what I recall.
It does. To avoid a penalty where the AI just memorizes the training data without actually learning, which we call overfitting, the dataset size needs to grow sublinearly with the model size.
Sublinearly, meaning what in practical terms?
Specifically, they found that if you increase the model size by 8 times, you roughly only need to increase the training data by about 5 times.
Which leads to something the sources call compute-efficient training. And honestly, that feels totally counterintuitive.
How so?
Well, if I'm paying millions of dollars for supercomputers, my instinct is to train a model until it's absolutely perfect. But the math says that's the wrong approach.
It is the wrong approach, yeah. If your goal is pure efficiency, and you have a massive but fixed budget for computing power, the optimal strategy is actually to build a very, very large model, feed it a relatively modest amount of data, and then intentionally stop the training process significantly short of convergence.
You don't train it to perfection.
No, you don't.
So you basically build a massive brain, show it just enough of the internet to get the underlying patterns, and then pull a plug and move on.
Exactly. And that philosophy is exactly what birthed GPT-3.
Wow.
The second paper, Language Models or Few-Shot Learners, details how OpenAI took the transformer and scaled it up to 175 billion parameters.
175 billion.
Yeah. At the time, that was 10 times larger than any non-sparse model ever created. And because of this unprecedented scale, they unlocked a phenomenon that totally disrupted the industry.
In-context learning.
Yes. It's called in-context learning.
And this is a huge paradigm shift. Let's make sure we really highlight this for you listening. Before this 175 billion parameter beast, if you wanted an AI to translate French, you had to physically alter its internal weights by training it on thousands of French translation examples.
Right. A very tedious process called fine-tuning.
But with GPT-3, the model had seen so much text during its pre-training that you didn't need to retrain it at all.
You didn't touch the weights. You just typed a prompt.
Right.
If you gave it 2 or 3 examples of English to French translation right there in the text box, it suddenly just adapted to the task on the fly. That is few-shot learning.
The sources mentioned they tested it on the Lambda benchmark, right? Which tests long-range dependencies in text, basically predicting the last word of a long passage.
Yeah.
And GPT-3 achieved 76% accuracy, 0 shot, meaning they give it 0 examples of how to do the test, and it just aced it anyway.
It's incredible. And if we connect this to the bigger picture, for you listening, this paper is exactly why you can log into a chatbot today, type, write me an email to my boss asking for vacation, but make it sound like a pirate, and it just works instantly.
Yes.
It completely shifted the entire AI industry from a paradigm of training and fine-tuning to the era of prompting.
But as we all quickly learn, raw, unguided power has a dark side.
Oh, definitely.
A giant model trained on the open, unfiltered internet learns absolutely everything. Yes, it learns grammar, facts, Shakespeare. But it also absorbs the toxic, the highly biased, the fraudulent, and just the completely unhelpful corners of the web.
And by default, remember, it is just a raw text predictor. It has no moral compass.
Right.
If you prompt a raw GPT-3 model with how do I build a chat, it might helpfully suggest a birdhouse. Or because the text exists somewhere in its vast training data, it might suggest something incredibly dangerous.
Which brings us to the third step of our AI blueprint, the manners.
The manners, yeah.
We have this chaotic, hyper-intelligent text predictor. How do you turn it into a polite, safe, helpful assistant? This is covered in the paper, Training Language Models to Follow Instructions with Human Feedback.
Better known as the Instruct GPT paper.
Right. So what was the core issue they were trying to solve here?
Well, the Instruct GPT paper identified a fundamental misalignment of objectives. The language modeling objective, just predicting the next token based on internet probabilities, is completely misaligned with what a user actually wants.
Which is an assistant that safely follows instruction.
Exactly. To fix this, they introduced a technique called reinforcement learning from human feedback, or RLHF.
Now, I've heard RLHF described as a parenting phase. Like the AI is a genius child who learned language by reading the entire internet alone in a room, and RLHF is the parent teaching it basic manners.
That's a great analogy.
But the paper gets quite mathematical. The sources mention an algorithm called PPO. To be honest, my eyes glazed over a bit at that part. What is that actually doing?
Let's break it down without the dense jargon. PPO stands for Proximal Policy Optimization. Think of the whole RLHF process as a game where the AI is trying to maximize its score.
Like a game.
First, human labelers sit down and write out ideal, safe responses to various prompts. The model practices on this. Then the model generates several different responses to a single prompt, and humans rank them from best to worst.
So the humans are saying, you know, response A is helpful, response B is toxic, response C is just gibberish.
Exactly. And that ranking data is used to train a separate, smaller AI called a reward model.
Okay,
This reward model basically acts as an automated judge.
I see.
Finally, the main language model plays the game using PPO. PPO is the algorithm that adjusts the AI's internal compass, teaching it to chase the highest possible score from the reward model.
Oh, so it's constantly trying to please that automated judge.
Right, while making sure it doesn't deviate so wildly that it forgets how to speak English properly. They are mathematically enforcing preferences for outputs that are helpful, honest, and harmless.
And what blew my mind in the sources was the cost of this alignment phase. The paper discusses the alignment tax.
Yes.
Usually we think of making complex systems safe as this massive, expensive, bureaucratic burden, but the computational cost of this RLHF phase is shockingly small compared to the raw training phase. Let's talk petaflops for a second.
Yeah, the numbers here are staggering. To give some context, a petaflop is a quadrillion of floating point operations per second.
Quadrillion.
It is a massive unit of computing power. If you ran one petaflop on a high-end consumer laptop, it would take thousands of years.
Wow.
Training the initial 175 billion parameter GPT-3 required a staggering 3,640 petaflops per second days.
3,640, okay, and the alignment phase, the parenting phase.
Training the supervised fine-tuning model for Instruct GPT required just 4.9 petaflops per second days.
4.9. That is literally a fraction of the cost.
It is. And this was a massive revelation for the economics of AI. It proved that tweaking a model's behavior, aligning it to human intent, is vastly cheaper than building a larger model from scratch.
That makes total sense.
Furthermore, the paper found that a 1.3 billion parameter Instruct GPT model, which is over 100 times smaller than the giant GPT-3, was actually preferred by human evaluators over the unaligned giant.
So alignment isn't just a safety checkpoint. It is a massive multiplier for actual utility.
Exactly.
Okay, so following our blueprint here, we built the transformer engine, we used scaling laws to make it massive, and we used RLHF to teach it manners.
Right.
We now have a hyper-efficient, massive, and highly polite AI. But there's still one glaring problem. Its knowledge is frozen in time.
Yes, the knowledge cutoff.
If its training data stopped in 2023 and you ask it about the news today, it doesn't know. And worse, because it's fundamentally a text predictor, it doesn't like to admit ignorance. It just confidently makes things up.
Hallucination.
So how do we fix its memory?
This brings us to the final piece of our puzzle, the fifth paper. Retrieval Augmented Generation for Knowledge-Intensive NLP Tasks.
Which we commonly call RM.
Yes. This paper explains how we solve the hallucination problem by giving the AI access to real-time external facts.
Okay, here's where it gets really interesting, but I have to play devil's advocate for a second.
Go for it.
If the model already has 175 billion parameters acting as this massive sponge holding all this internet knowledge, isn't strapping an external search engine to it a bit redundant? Like, why not just inject more facts directly into the parameters?
It's a great question, but the issue lies in how neural networks actually store information. The knowledge stored within those 175 billion parameters is what we call parametric memory.
Parametric memory, okay.
It is essentially a black box of probabilities. The model knows that Paris is the capital of France, but we can't easily look inside the mathematical weights to see exactly where it learned that.
Right.
More importantly, if a fact changes, say a country changes its capital, we can't easily reach into the black box and update that single fact without triggering expensive retraining.
Right, you can't just open the hood, find the capital city neuron, and flip a switch.
Precisely. RI solves this by combining the AI's internal parametric memory with non-parametric memory.
And what is that?
Think of non-parametric memory as a massive, explicitly searchable index of documents, like a dense database of Wikipedia articles or company policy manuals.
So how does the workflow actually change when I ask a ARGene-enabled model a question?
When you ask a question, the model doesn't just immediately guess from its internal weights. First, a pre-trained neural retriever searches the external index for relevant passages.
Okay.
Then it takes those retrieved documents and feeds them to the generator. The AI then synthesizes the final answer using both its internal linguistic fluency and the specific hard facts it just retrieved.
So it's the ultimate open book test. It doesn't have to memorize the entire encyclopedia during that expensive 3,600 petaflop pre-training phase.
No, it just needs to know how to read the encyclopedia and summarize the right page for you when you ask.
Yes, and this provides something crucial that businesses and researchers desperately need, right? Provenance.
Exactly, provenance. Because the model retrieves specific documents to base its answer on, we can trace exactly why the AI made a certain claim.
That's huge.
If it says a specific historical event happened on a Tuesday, we can see the exact paragraph it pulled that from.
And from an engineering standpoint, the sources mentioned you can hot swap this external index, meaning if I'm running a business, I don't need to spend millions of dollars retraining a language model every time my company's HR policy changes.
Right, you just update the text files in the retrieval database, and the AI instantly answers questions using the new rules.
For you listening, this is exactly why enterprise chatbots and customer support systems actually work today without constantly lying to you. RKG grounds the fluent, polite text generation of the AI in verifiable, updatable reality.
It is an incredibly elegant solution. By separating the reasoning engine from the memory storage, RKey makes AI practical, factual, and economically viable to maintain.
Okay, we've covered a tremendous amount of ground today. Let's sort of synthesize this journey. If you want to understand modern AI and you want to cut through the hype, it really boils down to this four-step formula mapped out by these foundational papers.
Right.
First, you build a parallel engine, the transformer architecture, that uses queries, keys, and values to weigh context simultaneously.
Second, you use the brute force of scale discovered through scaling laws in GPT-3 to make the model massive and unlock its ability to learn just from a text prompt.
Third, you initiate the alignment phase, instruct GPT in the RLHF process to mathematically teach it manners and safety.
And finally, you give it the open book test brag so it can reference external up-to-date facts instead of hallucinating.
It really is a remarkable blueprint. When you break it down into these distinct scientific breakthroughs, the magic disappears, but the sheer engineering brilliance becomes even more apparent.
It does.
So what does this all mean? We have the map. We see exactly how the pieces fit together to create the AI systems we use every single day. But where does this map lead us next?
This raises an important question to leave everyone with. If these 5 papers perfectly map out the past decade of breakthroughs, building the engine, scaling it, aligning it, and giving it a reference library, what is the next missing puzzle piece? If the AI is already an aligned, perfectly read assistant that can retrieve human knowledge flawlessly, what happens to society when the architecture evolves from just retrieving and summarizing human knowledge to actually conducting its own original research?
Wow. That is a staggering thought. I mean, the library we walk into at the beginning of this deep dive right now, that AI is just the ultimate librarian helping us find the books. But pretty soon, it might be
Yeah.
the one writing the books that no human has even thought of yet.
Exactly.
Something to think about next time you type a prompt.